morning, everyone. Thank you so much for coming to my talk. I'm very excited to show you some of the work that I've been doing with my research group at MIT on natural disaster forecasting using machine learning. So, quick introduction about myself. I'm a final year PhD candidate from Operations Research Center from MIT. And my research focus has been on using machine learning models for climate change adaptation. And you can read all of my work in the website with the QR code. And today, I'm very honored to be here. Thanks so much, Patrick and Cyprian, for the invitation. So I'm here to talk about natural disaster forecasting. I guess the first half of the talk has primarily been on data processing, specifically the satellite images. And I guess today the focus of my talk is about more on the temporal domain of forecasting natural disasters, both short-term and long-term. So here is the kind of the data about why we should be caring about this problem. We're seeing tremendous growth of the number of natural disasters worldwide, and because of climate change, we're living in a more extreme climate regime, and dealing with them is going to be a task that we cannot avoid as a society. They're not only extremely deadly in terms of costing human lives, destroying communities, as we see flooding events in Pakistan, Bangladesh, but they're also extremely expensive to fund. For example, these are all of the total costs of these natural disasters in aggregate in the United States since 1980s. And we see that every single one of these events is extremely expensive. And currently, the most of the approach that we have in response to natural disaster has been, there is a natural disaster happening, and then we try to save as many lives as possible. Kind of one of the questions that I ask myself as a researcher is that can we do better than just very responsively act towards those natural disasters? Because of all of these new technologies, can we kind of do some preventative work to basically to reduce all of these responsive costs? So the primary goal around a lot of the work that I've been doing has been using machine learning and optimization tools to facilitate climate change adaptation, to build resilience around communities, and to aid sustainable development. And how do we do that? One of the ways of using new technologies has been forecasting. So therefore, when we talk about weather forecasting, I think that it would be reasonable to think about how we get here as a field of domain in terms of weather forecasting. I'm a big fan of history, so I always like to think about the historical aspect. So weather forecasting has been as ancient as human civilization. So as early as 300 BC, Aristotle has been pondering about his theories about how the formation of clouds and rain forms. And at the same time, Chinese astronomers has invented this festival calendar in which they divided the whole year into 24 periods, each of which has a specific climate regime. So later, as we kind of develop better scientific methods for measuring capabilities and also the development of atmospheric sciences, we come to the understanding of the physical laws for the underlying atmospheric interactions. And that led to the idea of what we call right now dynamical modeling. So these are physics-based models that simulate what weather is happening. And basically, since a century ago until now, these models have primarily been the major models that drive the current field of weather forecasting. But interestingly, though, the first dynamical model was coined in the early 1904, and it took Richardson alone. He was working alone by hand, doing all of the physical simulations. It took him several months to do a very wildly inaccurate 6-hour weather forecasting outside of Munich. So obviously that was not possible until the modern introduction of modern computers in the 40s that allowed us to do proper weather forecasting. So basically, as I mentioned, these weather forecasting models that are physical models are extremely expensive to compute, and they're basically based on simulation. And that led to the development of machine learning model as a new frontier for this approach. I'm sure that you've all read about this paper, GraphCast, from DeepMind, that basically shows that a lot of the common tasks could be outperformed by machine learning models. And interestingly, though, at this point, I kind of think that history kind of went in a circle because, in early history, when we didn't have physical understanding, a lot of Aristotle and Chinese astronomers, they derived the formation from patterns. And now, with machine learning, it's a very similar approach. We're doing pattern recognition. So although I think that what a lot of the work that I've been doing may offend certain physicists in the field, and they think that, it's just a black box and, you're not really understanding the laws, I would say, yes, but look, we're not the first one to do so. So I guess the reason that why we can do this right now, the concept is not new, but right now we can do this better is thanks to computing power, data availability, as we were talking about, a lot of availability of satellite data and processing techniques. So I recall that back in the days when we started working on this about 5 years ago, when I just started my PhD, getting satellite data was extremely difficult. It took us almost several months to just download the data and convert it into a different format. But now, 5 years later, everything is much more streamlined and everything is much easier. And thanks to the development of foundational models, a lot of the processing time could be reduced as well. And kind of because of all of the subfields of computer vision and natural language processing, and also development in time series analysis, and specifically foundational models across all of these domains, that's why we're kind of right now interested in doing multimodal machine learning, which is in essence about how do we combine images with language data, with time series data all together to make better forecasts. So essentially, when we think about combining data modality, we're really thinking about fusing data. And fusing data by itself, as a field, there are generally three approaches, which encompasses a lot of different approaches, obviously. So there's the early fusion, which is more of an end-to-end pipeline. You put all of the data into one model, and the model, like for example, a deep learning architecture, that give you an output. And there's the late fusion, which is basically ensemble models. So you train models based on different modalities of data, and then you take a kind of a weighted average consensus based on these models. And finally, there's the in-between, which is mid-fusion. And this is what I'm going to talk about today. So based on our research experience, we kind of gravitated towards a mid-fusion approach. And the reason is, so broadly speaking, here's the framework of a mid-fusion approach. We process data separately, individually, and then we concatenate them in the feature space. And then we use the feature space, the concatenated embeddings, to make the downstream predictions. And why this is why this is a good approach. Firstly, we are able to leverage state-of-the-art foundational models in different domains, in language, in satellite images, etc. And secondly, we can leverage state-of-the-art forecasting models in the downstream task, which would allow us to do, achieve different goals based on different interests. For example, if we're interested in interpretability, then we can leverage a lot of the already existing techniques in interpretation to kind of understand, for example, what features are important and what are not. So the first application that I'm going to talk about today is on hurricane forecasting. The reason that we chose to forecast hurricane is that it is one of the most notorious tasks in the field of meteorology and is extremely chaotic. Specifically, we need to do track and intensity forecast tasks in the field of hurricane forecasting. So here is an kind of an illustration. So on the left-hand side, we see this is kind of what the goal should be in terms of from a practitioner's perspective. So we're interested in the task, in the track and intensity tasks. So hurricanes are rapidly evolving storms that originates from the sea. We're interested in where it's going because we need to evacuate communities. And we also need to know how intense it is because that determines the magnitude of evacuation. And typically on news, on the right-hand side is a picture showing what typically is weather hurricane forecasting in the news. And in the field, it's called a spaghetti model. The reason being, each of the line you see that generates, it's forecast generated by one model. And typically, these models are different dynamical models based on different, granularities and different data sets. And for this task, we took a multimodal approach with two data modalities. So we took the traditional tabular historical data that includes basically features from hurricanes. And in addition, we took satellite images, which are given as reanalysis maps. So reanalysis maps are basically observations of the wind speed. In this case, we used the U, V, and Z component of the wind from 3 pressure levels or atmospheric levels. So basically, it's a kind of a 3-dimensional tensor object at each time component. And in particular, our kind of pipeline consists of 3 steps. So we have the data processing step where we process data individually is with vision data given as reanalysis maps and also statistical data. And we concatenated the embeddings and then we did the downstream forecasting. In particular, we tried 2 different types of vision embedding architectures. So on the left-hand side, we have a deep learning approach with encoder, decoder. And so basically at each time step, we're interested in the next 12 hours track and intensity of the hurricane. And at this time step, we took the past 24-hour data given at 3 hours interval. And each time step of interval, we had a 3-dimensional reanalysis map data. So in the end, it was a very high-dimensional problem, and we kept the time-temporal component by kind of treating that in the transformer encoder architecture. And basically, we did this work about 4.5 years ago. At the time, foundational models were not available. So if you were to ask me if I were to do this now, I would probably try to use some IBM models to kind of speed up the processing, the feature extraction part. But nevertheless, so in addition, we also tried tensor decomposition, which is more of an unsupervised learning approach. It is faster because it's more analytics-based. So here are some of the results. Because of the this presentation is not so long, so I only give one out of sample results because I was told to avoid showing tables in presentations. So here I'm showing the out of sample intensity forecasting for 12 hours, and this is the only table, so you only have to focus right now. I'm displaying the mean absolute error with a standard deviation in brackets, and the unit is in knots, which is the standard unit for wind forecasting. We separated it into North Atlantic Basin as well as Eastern Pacific Basin because the behavior of hurricanes are very different in these two basins. And typically, dynamical models would be developed individually for two basins, but in this case, we just have one model actually for both basins. So here you see that what we see here, so the first 3 lines are all machine learning approaches, and the last 3 lines are all standalone operational forecasts. So operational forecasts are typically maintained by weather forecasting agencies, and they're typically take 4 to 6 hours of simulation time to produce these forecasts. And HWRF and GFSO are the most advanced dynamical models. So what we see here is that, taking a machine learning approach, we're having very competitive results with the most advanced operational models. In particular, we're slightly better in Eastern Pacific Basin and less good in North Atlantic Basin. However, it is worth noting that, like all machine learning models, the training time for those machine learning models are huge and they're more front-loaded. However, the deployment time is extremely fast. So these are really, kind of results to show the concept, and I don't claim that our model can make real-time forecast because we used reanalysis maps. So people in the field may know that reanalysis maps are mutually available maps, and as researchers, these are the best quality open source satellite maps that we have access to. So all of these models are trained on data that is actually available maybe 6 hours plus after the real-time wind. But nevertheless, these results suggest that these approaches are very promising, and proper models should be trained on using real-time data. So the key lessons learned from this work is that multimodal machine learning typically outperforms single modal approaches if you use only satellite images, for example, or using statistical data. And secondly, we produce very competitive results that shows very promising prospects down the road. And finally, actually, what is very interesting to me is that can we take a machine learning approach to think about longer term forecasts? If not, right now it's hours, but can we do it months or even years in advance? And if so, what does that mean to think about insurance, urban planning, infrastructure development? Can we take more preventative measures to mitigate these impacts before they actually happen? So that's all, and thank you very much for your time and attention. Very happy to take questions.
So we have time for a few questions. Yes.
Thank you for a great talk. I really enjoyed, especially the introduction where you talked about the history of weather prediction. And this is something I have never thought about, but the works of von Neumann and Lyapunov and Kolmogorov and all of these guys who worked on like chaos or nonlinear dynamics was really culminated then with Ed Lawrence's discovery on meteorological systems, which was like birth of like chaos theory, which pretty much like opened up this completely new field, and we discovered kind of like higher symmetries or higher like physical laws. Do you think we should be also searching for those things with like models like GraphCast and Pangu, enabling us to look at very, very high dimensional data and searching for symmetries or physical laws that we could maybe extract from those, which would maybe completely revolutionize our understanding of climate and meteorology. Thanks.
Well, that's a fantastic question, and well, I think that it's a fantastic area to think about. How do we use these computing power to enable our understanding of the physical system? And for example, for things like more longer term, like climate, simulating climate, can we use these? So it is definitely, I think it's a pretty active area of research in terms of thinking about using machine learning and approaches to help us understand things that we are just too, it's just too complicated for physics models to, solve and to model them out. So I definitely think it's a very interesting domain. It would be fantastic to see what these models tell us. Mm-hmm. Thank you for your question, though.
We had another question here.
Yes, thank you. Thank you very much for the very good talk. I have an analogous question, and because you were opposing, if I understood you correctly, the dynamic models to your approach, the multimodal approach, do you think there is a way to combine the two, to basically use the dynamic models and then put a wrapper around it, or give new kinds of data to it or something, instead of opposing it?
Yeah, I definitely think there is a lot of interest in combining the two approaches. So one example, a very viable example, would be to use preliminary results from dynamical equations, for example, which are physically motivated, for example, that are getting the whole, to simulate the whole dynamical model would take a long time. But if you take preliminary features and feed them into machine learning model, that could really extremely help forecasting capabilities in my view. But obviously this would require collaboration with across fields, machine learning experts and meteorology experts. I definitely think this is a very viable way forward.